100 facts about the Milky Way galaxy. The moment you hear this story, you'll feel like you've stepped into another world. A world so vast and ancient that it stretches far beyond what the human mind can hold, and yet so familiar that it sits quietly above us every single night. This is the Milky Way galaxy. Not just a band of light across the sky, but the home of billions upon billions of stars, a place that has shaped myth, memory, and meaning for as long as people have looked upward. Tonight, we walk slowly into that quiet immensity. Every detail, every fact, is another stone on the long pathway through the stars. You will not find drama here or fast excitement, but instead the calm reassurance of something far older and steadier than ourselves. The galaxy drifts in silence, and we drift with it. As the minutes pass, you may notice time itself slowing down. The steady rhythm of stars being born, living their long lives, and fading into memory, mirrors the quiet rhythm of your own breath. Every fact becomes another step deeper into rest. Every description becomes another thread in a soft blanket of stillness. This isn't just a video. It's a doorway into peace. You step into the galaxy not to be overwhelmed, but to be carried gently into sleep. And once you step through, you may not want to leave. If this journey feels as magical to you as it does to me, make sure you hit that subscribe button so you never miss a moment. Leave a comment sharing your own experience or thoughts. I read every single one. And if this made you feel even a little inspired, give it a like. It helps more dreamers like you find us. The shape of the galaxy. When people look at the night sky, they often see only scattered stars, points of light that seem alone in the vastness. Yet, stretching above us, there is something larger and more complete, a pale band of brightness that has been noticed since the earliest days of human memory. This band is the Milky Way. To the naked eye, it seems like a misty ribbon, faint and fragile. Yet in truth, it is the light of countless stars, blended together by distance into a soft glow. The Milky Way is not simply a blur or a cloud. It is an immense structure, a galaxy, one among billions, but to us it is home. Its shape is not random, but ordered, formed by gravity and time. At its center rests a dense bulge, a spherical concentration of stars that have orbited together for billions of years. These stars are among the oldest in existence, their light reaching us as a quiet memory of the early universe. Crossing through this bulge is a bar, a stretched formation of stars and gas. The bar acts as a bridge, channeling material into the inner galaxy and helping to shape the spiral arms. The arms are the most familiar feature, vast curved lanes where stars and dust are drawn into long, slow patterns. They are not solid structures, but waves of density, places where matter gathers more thickly, producing the appearance of glowing arms. Our own star, the Sun, does not lie in the center, but in one of these arms, far from the crowded heart. It rests in what astronomers call the Orion Spur, a smaller offshoot of the larger Sagittarius arm. From here, we look inward toward the dense brightness of the bulge, and outward toward the thinner reaches of the galactic edge. This position gives us a perspective both near and far, part of the whole yet slightly removed from the core. Encircling the galaxy is the halo, a wide sphere of space where ancient clusters drift. These clusters are made of some of the oldest stars known, quiet remnants of the earliest stages of galactic formation. Though faint, they hold the record of times far older than our world, orbiting the galaxy's heart in slow, endless paths. Altogether, the Milky Way forms a disk roughly 100,000 light-years across. To cross it, even at the speed of light, would take 100 millennia. This immense disk is thin compared to its width, only about 1,000 light-years thick in the regions where most stars lie. Yet this thinness makes the galaxy appear as a narrow band when we view it from within, stretching across our sky as a soft, glowing arc. The spiral arms of the Milky Way are among its most striking features. From above, they would resemble long, sweeping curves that wind outward from the center, like the petals of an immense cosmic flower. These arms are not solid structures that one could walk along. Instead, they are patterns of higher density, created as stars and clouds of gas are drawn together in waves. Where matter is more concentrated, new stars are born, glowing brightly and briefly, lighting the arms with their radiance. Between the arms, the space is not empty, but the stars there are fewer and dimmer, leaving the arms to appear as the glowing lanes that define the galaxy's shape. Astronomers have given names to these spiral arms, identifying the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and others. The Sun and its planets belong to a smaller feature called the Orion spur. This spur is not one of the main arms but a branch, a quieter lane that lies between two greater streams of stars. Our view of the galaxy is shaped by this position. Looking inward, we see the brighter and denser regions closer to the core, where the stars are numerous and their light blends into a soft haze. Looking outward, the stars thin and the dark of intergalactic space becomes more apparent. The galaxy does not remain still. It rotates, slowly but steadily, carrying its stars around the center in vast orbits. The Sun itself moves at a speed of more than 800,000 kilometers per hour, yet the distances are so great that a single orbit takes around 250 million years. This means that during the entire history of the Earth, with all its ages of stone and fire, life and extinction, continents shifting and civilizations rising, our planet has completed only a handful of journeys around the galactic core. Time on this scale stretches far beyond human history, and the galaxy moves with a patience that seems eternal. The thickness of the galactic disk is another measure of its shape. Though the galaxy is 100,000 light-years across, the disk itself is only about 1,000 light-years thick. Within this narrow space lies the crowded plain of stars, gas, and dust. Above and below it, the halo extends much farther, but is so sparsely populated that it is nearly invisible. From within, this thinness is the reason we see the Milky Way as a narrow band across the sky. Were the disk thicker, the glow would spread more widely, but because it is slender, the light forms a confined ribbon, one that has guided and inspired observers across countless generations. The galaxy has been mapped not only through observation but through careful study of star positions and motions. With telescopes sensitive to many forms of light, radio waves, infrared, visible, and beyond, astronomers have traced the outlines of the arms, the bar, and the halo. Each wavelength reveals a different aspect of the galaxy. The hot young stars, the cool gas clouds, the hidden dust lanes, and the ancient stars that move slowly through the halo. Together these images form a composite picture, not seen from the outside but reconstructed from within, like assembling a portrait of a vast house while living inside one of its rooms. The distance from our Sun to the galactic center is another key part of the Milky Way's shape. Astronomers estimate that the Sun is about 27,000 light-years away from the core. To imagine this is difficult, but it means that even traveling at the speed of light, a journey from our world to the heart of the galaxy would take nearly 30 millennia. This location places us in a relatively quiet neighborhood, away from the busiest regions near the bulge, where stars are denser, older, and often less stable. Being set out in the Orion spur allows life on Earth to exist without the constant disruptions that might occur closer to the crowded galactic center. The appearance of the Milky Way as a band of light is directly tied to our position within this thin, wide disk. When we look toward the galactic plane, our line of sight passes through millions upon millions of stars, their combined light blending into a continuous glow. The dust and gas within the disk darken parts of the view, creating rifts and shapes that have inspired countless myths. Ancient cultures often described the Milky Way as a river of light, a pathway of spirits, or the road of the gods. What they were seeing was the structure of our galaxy, revealed as a faint but steady presence in the night sky. Rotation also shapes our understanding. The galaxy turns as a whole, though not like a rigid wheel. Stars closer to the center orbit more quickly, while those farther out move at different speeds. Yet, because of the way gravity works on such scales, the spiral arms themselves maintain their form. This motion has been ongoing since the earliest days of the galaxy's history, and it will continue for billions of years more. Each orbit of the Sun is a galactic year, and though it is too long for us to ever notice, it marks the slow rhythm by which the Milky Way evolves. The mapping of the galaxy has been a gradual process, pieced together over centuries. Early observers could only see the band of light and speculate on its nature. With the invention of telescopes, the hazy glow resolved into countless stars. Later, as technology advanced, astronomers learned to measure distances, to chart positions, and to recognize the spiral form hidden in the vastness. Radio telescopes revealed the distribution of hydrogen gas, tracing the arms. Infrared studies pierced the dust to glimpse the bulge and bar. Space observatories like Gaia have cataloged the motions of billions of stars, allowing scientists to construct the most detailed map yet of our galactic home. Even so, the picture remains incomplete. We live inside the system we study, and so our view will always be limited, like examining a forest while standing among its trees. The Milky Way is both vast and delicate, immense in size but subtle in appearance. Its shape is defined not only by stars, but by the invisible matter that surrounds it, the dark halo that provides the mass needed to hold it together. Though unseen, this dark matter gives the galaxy its structure, allowing the arms to remain and the disk to stay intact. Without it, the Milky Way would fly apart. In this way, the galaxy's shape is more than what we can see. It is also what we cannot see, the hidden framework that holds everything in place. The galactic bulge itself deserves more quiet attention. At the heart of the Milky Way lies this swollen sphere of stars, stretching thousands of light-years across. Unlike the spiral arms, which hold younger and more varied stars, the bulge is dominated by old, reddish suns. Their light is softer, their fuel nearly spent, but together they create a dense and glowing core. The bulge is not uniform. Observations show that it has a bar-like shape at its center, stretching across it like a hidden spine. This bar channels streams of gas toward the center, fueling star formation in the crowded regions near the core. Surrounding the bulge is the disk, the broad and thin layer that forms the main body of the galaxy. Here, most of the Milky Way's stars, gas and dust reside. The disk is where the spiral arms unfurl, where new stars are born, and where the Sun makes its slow orbit. Its thinness compared to its width gives the galaxy its pancake-like structure, and from our position inside, it is the reason the Milky Way forms a band of light in the sky. Within this disk, lanes of dark dust wind like rivers, blocking starlight and dividing the bright patches of the sky. These dust lanes are as much a part of the galaxy's shape as the stars themselves, marking the places where light is hidden, but also where future stars may one day emerge. Beyond the disk and bulge lies the halo, a vast and faint envelope of space. Here, stars are sparse, but ancient clusters known as globular clusters still orbit. These clusters contain some of the oldest stars in the galaxy, nearly as old as the universe itself. They circle the galactic center in long, slow arcs, forming a loose sphere that extends far above and below the plane of the disk. Invisible within the halo is dark matter, the unseen mass that outweighs the stars and gas combined. Though it cannot be observed directly, its presence is known by the way it holds the galaxy together, giving the Milky Way the shape it has. The size of the Milky Way makes it one of the larger galaxies in the local group. From edge to edge, the disk spans about 100,000 light-years, though some studies suggest it could be even larger, extending as far as 200,000 light-years when the faintest stars are counted. The Sun, as one of hundreds of billions of stars, circles this vast expanse in an orbit that takes hundreds of millions of years to complete. The galaxy's size is not only a measure of its immensity but also a reminder of the scale of time. For distances this great are bound to times that stretch beyond any human frame of reference. To understand the Milky Way is to recognize that we see it not from the outside, as we might see a distant spiral galaxy through a telescope, but from within, from one small corner of its vast disk. This position shapes our perspective. When we gaze toward the galactic center, we look across tens of thousands of light-years, through layers of dust, gas, and star clouds. The result is a region dense with light, broken by dark rifts where dust blocks the stars behind. When we look away from the center, toward the edges of the disk, the stars thin, and the glow fades into the darker reaches of intergalactic space. In every direction, however, the shape of the galaxy determines what we see, quietly guiding our view even when we do not realize it. The Milky Way is not frozen in its form. Its structure has evolved for billions of years and will continue to shift. The spiral arms are not permanent features but patterns that persist across immense stretches of time. The bulge has grown denser as stars aged within it, and the halo carries the traces of ancient collisions, where smaller galaxies were absorbed into our own. Even the Sun, in its orbit around the center, will eventually pass through different arms and regions, each with its own character, each changing the view of the sky across eras too long for us to measure directly. To describe the shape of the Milky Way is to describe not only a structure but also a rhythm. The bulge, the bar, the arms, the disk, and the halo are like instruments in a vast orchestra, each playing its part across cosmic time. From our place in the Orion Spur, we hear only the faintest echo of this harmony. Yet it surrounds us always, steady and unchanging to the human eye. The galaxy is a disk of stars, one among many, but to us it is the framework of everything we know. The quiet home where Earth drifts, one star among billions, circling endlessly in the soft, slow dance of the Milky while the stars of the galaxy. The Milky Way is not simply a disk of light and dust. It is above all a collection of stars, so numerous that to count them is beyond human possibility. Astronomers estimate that the Milky Way contains between 100 billion and 400 billion stars. The wide range reflects the uncertainty of measuring something so immense, for stars vary in brightness, and the faintest of them can be hidden by dust or distance. Yet even the lowest estimates reveal a number that defies imagination. To think of 100 billion stars is to think of 100 billion suns, each one its own system, each one carrying with it the possibility of worlds. Among these stars there is great diversity. Most are small and faint, cooler than our sun, known as red dwarfs. These stars burn slowly, lasting for trillions of years, far longer than the universe has yet existed. They are humble and steady, quietly filling the galaxy with light that the human eye cannot easily see. Others are larger and brighter, like blue giants and supergiants. These live briefly and burn fiercely, their light visible across vast distances, but their lives end in violent collapse. Between these extremes lie stars like our Sun, yellow dwarfs, steady and moderate, living long enough to allow the slow unfolding of life on the planets that circle them. The Sun itself is ordinary when seen against the background of the galaxy. It is neither the largest nor the smallest, neither the brightest nor the dimmest. Its value lies in its stability, in the quiet and regular burning of hydrogen into helium, a process that will continue for billions more years. To us, it is the center of everything, but to the galaxy, it is only one among hundreds of billions, a small star drifting in the Orion spur. Its ordinariness is part of its comfort, for it reminds us that the galaxy is filled with stars like ours, countless points of light repeating the same patterns, sustaining the same quiet cycles. Not all stars drift alone. Many gather into groups called clusters. These clusters come in two main forms: open clusters and globular clusters. Open clusters are loose associations of younger stars, formed together from the same cloud of gas and still bound, at least for a time, by gravity. They may contain a few dozen to a few thousand members, shining close to one another in the plane of the galaxy. Over time, many of these stars drift apart, joining the wider disk, but while they last, they are families of light, still connected to their shared origin. Globular clusters, by contrast, are ancient and dense. They are spherical gatherings of hundreds of thousands of stars, compact and brilliant, circling the galaxy in its halo. Their stars are among the oldest known, survivors from the earliest stages of the Milky Way's history. To look at a globular cluster is to look back into time, into the steady glow of suns that have burned for more than 10 billion years. These clusters move slowly around the galactic core, above and below the disk, silent witnesses to the changes of countless ages. Stars are also distinguished by what astronomers call their metallicity, the presence of elements heavier than hydrogen and helium. Younger stars, like those of the spiral arms, tend to have higher metallicity, enriched by the generations of stars that came before them. Each time a massive star dies in a supernova, it scatters heavy elements into space, which are then gathered into the next cycle of star formation. Older stars, particularly those in the halo and bulge, have very low metallicity, their compositions reflecting the universe before many of the heavier elements existed. These chemical differences are quiet markers of time, allowing astronomers to trace the history of the galaxy through its starlight. Within the galaxy, stars also differ depending on their location. In the bulge, the central sphere, stars are older, redder, and more tightly packed. In the disk, stars are more varied. Young blue stars, older yellow suns, and countless dwarfs mingling together in the spiral arms. In the halo, stars are sparse and ancient, drifting in long solitary paths. Each region has its own character, shaped by history and environment, yet together they form the living whole of the Milky Way. Among the stars of the Milky Way, some stand out for their great age. These are the oldest stars, survivors from the early days of the galaxy, still burning after more than 13 billion years. Many of them are found in the halo, their faint light drifting far from the crowded arms. They are small and long-lived, red dwarfs and other low-mass stars that consume their fuel slowly, stretching their lives across cosmic time. Their presence is a reminder of the galaxy's ancient origins, for they carry within them the chemical signatures of an earlier universe, formed before the heavier elements were common. To study these stars is to touch the beginnings of the Milky Way itself. Not all stars shine with steady light. Some are variable stars, their brightness changing over time. The reasons for this vary. In some, the star expands and contracts, pulsing as its outer layers shift in rhythm. In others, eclipses from companion stars cause the light to dim and brighten. These changes, measured carefully, have become important tools in astronomy. Cepheid variables, for example, serve as cosmic markers, their regular pulsations linked to their intrinsic brightness, allowing astronomers to measure distances across the galaxy. Yet beyond their scientific value, they are simply another expression of the diversity of stars, points of light that flicker gently, their rhythms unfolding in silence. Binary stars are another common feature of the Milky Way. Many stars do not travel alone, but orbit a partner. Some systems contain two stars of similar mass, circling one another in long, graceful arcs. Others pair a larger star with a smaller companion, their movements reflecting the balance of their unequal weights. In some binaries, the stars are so close that they share matter, their lives intertwined until one consumes the other. In wider systems, they circle distantly, companions that remain bound through the ages. Multiple star systems exist as well, with 3 or more stars connected by gravity in intricate patterns. To us, they may appear as single points of light, but in truth they are families of suns, bound together across the quiet of space. Even as stars age and die, new stars are constantly being born, continuing the quiet cycle of the galaxy. These places of birth are known as stellar nurseries. They are vast clouds of gas and dust, often stretching for dozens or even hundreds of light years. Within these clouds, gravity gathers material into clumps, slowly drawing them together until the pressure and heat grow strong enough for nuclear fusion to begin. From these beginnings, new stars emerge, glowing first as faint embers, then brightening into suns that will endure for billions of years. One of the most famous examples of such a region is the Orion Nebula, visible even to the naked eye as a misty patch in the sword of the constellation Orion. This nebula is a living reminder that the galaxy is not static but alive with constant renewal. Stars form, shine, and eventually fade, and in their passing they enrich the galaxy with the materials needed for the next generation. The spiral arms are especially rich in these nurseries, for they are the places where gas and dust are compressed most strongly. These arms are not only beautiful structures but the cradles of the stars that light the Milky Way. The process of star formation links past, present, and future. The oldest stars still shine faintly in the halo, carrying memories of the early universe. The youngest stars blaze brightly in the arms, announcing the freshness of their birth. Between them lie stars like the sun, steady and enduring, providing light and warmth across billions of years. Together, these different stages form the living body of the galaxy, a collection of stars at every moment of life, scattered across 100,000 light-years of space. In the quiet rhythm of the Milky Way, stars are born, they shine, and they fade. Their light reaches us across distances so great that to see them is to see into the past, to glimpse events that happened thousands or millions of years ago. To rest beneath the night sky is to lie under the glow of billions of histories, each star a record of time passing in silence. The galaxy is not simply a structure of arms and dust, but a vast community of suns, each one part of the great harmony that defines the Milky Way. Nebulae and gas clouds, the Milky Way is not only a collection of stars. Between the stars lies a quieter, more delicate presence, vast clouds of gas and dust that fill the galaxy. Though invisible to the naked eye in most cases, These nebulae are the raw material from which stars are born, the remnants of stars that have died, and the soft fabric that shapes the appearance of the spiral arms. One kind of nebula is called an emission nebula. These are regions where young, hot stars shine so strongly that they cause the surrounding gas to glow. The gas, often rich in hydrogen, becomes energized by the ultraviolet light, and the atoms release their energy as visible light, producing the soft red glow seen in many photographs of nebulae. These glowing clouds are nurseries of stars, their light marking the places where new suns are being formed, adding to the population of the galaxy. Another kind of nebula is the reflection nebula. These clouds do not glow on their own but instead reflect the light of nearby stars. Their colors are usually soft blues, caused by the scattering of starlight by fine dust particles, similar to the way Earth's sky appears blue. Reflection nebulae are quieter in appearance, less brilliant than emission nebulae, but they are equally important in shaping the galaxy's soft texture. They reveal the presence of dust and gas, showing us where the interstellar medium quietly drifts. Planetary nebulae form another category. Despite their name, they have nothing to do with planets. They are created when dying stars, like the sun in its far future, shed their outer layers. The star's core remains, glowing faintly as a white dwarf, while the expelled gas drifts outward, illuminated by the remnant star. Planetary nebulae are often symmetrical, forming rings, shells, or bubbles that expand slowly into space. They are short-lived compared to the galaxy's age, lasting only tens of thousands of years, but they play a role in returning material to the interstellar medium, enriching it for future generations of stars. When stars more massive than the Sun reach the end of their lives, their deaths create supernova remnants. A supernova is one of the most powerful events in the galaxy, but here we will describe it in its quiet aftermath. After the explosion, the outer layers of the star are thrown into space, expanding outward as a vast shell of gas and dust. Over thousands of years, this material cools and spreads, becoming part of the interstellar medium. What remains is a delicate structure of glowing filaments, often shaped into rings or wisps that drift like smoke across the darkness. These remnants are reminders that stars both give and take, ending their lives in ways that provide new material for the galaxy's future. Even larger and more significant are the molecular clouds. These are the coldest and densest parts of the interstellar medium, where atoms bond into molecules, most often molecular hydrogen. Unlike emission nebulae or reflection nebulae, molecular clouds are usually dark. Their dust absorbs light, making them appear as black shapes against the brighter background of stars. Yet these dark clouds are the birthplaces of new stars. Inside them, gravity gathers the cold gas, compressing it until the heat of fusion begins. They are quiet regions, hidden from sight, where the next generations of stars and planets slowly take shape. One of the most famous examples of both emission and molecular clouds lies close to us, the Orion Nebula. To the naked eye, it appears as a faint smudge in the sword of Orion. With telescopes, it reveals a vast region of gas and dust, glowing with the light of newborn stars. It is both a nursery and a laboratory, a place where astronomers can observe star formation in progress. The Orion Nebula is only one among many such regions, but its nearness allows us to glimpse the processes that, on larger scales, occur across the galaxy. The Milky Way's disk is not only a collection of stars but also a reservoir of gas. This gas, mostly hydrogen and helium, makes up about 10 to 15% of the disk's mass. Spread thinly across immense distances, it is rarely visible on its own. yet it plays a quiet, essential role. Without it, there would be no new stars, for the gas is the raw material from which stars are formed. In some regions it is scattered, thin, and almost transparent. In others it gathers into denser clouds, waiting for the slow pull of gravity to bring it together. These regions of denser gas are known as star-forming regions. They are scattered throughout the spiral arms, where the waves of density compress the clouds and trigger collapse. Within these regions, clusters of stars emerge, often accompanied by nebulae that glow or reflect light. From a distance, these places appear as bright knots or glowing patches within the arms. They mark the places where the galaxy renews itself, creating new light to replace the stars that fade away. Though the process is vast and slow, it is continuous, ensuring that the Milky Way remains a living system rather than a fading one. Running through the spiral arms are also dark features known as dust lanes. These lanes are made of tiny particles, grains of carbon and silicates, mixed with gas. They absorb and block starlight, creating dark streaks against the brighter background. To the human eye, these dust lanes can make the Milky Way appear broken or divided, with dark rifts cutting across the glow. Yet they are not emptiness, but fullness, concentrations of matter that hide light behind them. Within them, stars may be forming unseen, their birth veiled by the very material that makes it possible. Together, the gas, the dust, and the nebulae form what astronomers call the interstellar medium. It is the quiet fabric of the galaxy, filling the spaces between stars, shaping what we see and what we do not. It is not uniform. It is patchy, varied, and constantly in motion, stirred by the birth and death of stars. Without it, the Milky Way would be static. With it, the galaxy breathes, shifting slowly as matter cycles from star to cloud and back again. The nebulae and gas clouds of the Milky Way are more than scenery. They are part of a larger rhythm, a cycle that has continued since the earliest ages of the galaxy. Stars are born within these clouds, live for millions or billions of years, and then return their material to space when they die. The gas and dust released in planetary nebulae, in supernova remnants, or in stellar winds does not disappear. It drifts outward, cools, and becomes part of the interstellar medium once again. In time, gravity gathers it, compresses it, and gives rise to new stars. This cycle is sometimes called the ecology of the galaxy. It is not life in the sense we know on Earth, but it is a process of renewal. Matter is recycled, transformed from one form to another, endlessly reused in different generations of stars. The atoms in our bodies, the carbon, oxygen, calcium, and iron, were once forged in stars, carried into space, and gathered again into the cloud that became the sun and planets. We are part of this quiet exchange, a continuation of the same pattern that governs the galaxy. The role of nebulae and clouds in this process is both practical and poetic. Practically, they are the reservoirs of raw material, the hidden banks where the elements are stored. Poetic, because they form the visible traces of the galaxy's slow breathing, glowing softly or blocking light in ways that remind us of both presence and absence. They are not permanent. Emission nebulae fade when their stars move on. Planetary nebulae disperse into the medium. Supernova remnants expand until they vanish. Yet the process does not end. Each fading cloud contributes to the next, a continuity that extends far beyond human time. When we look at the Milky Way in the night sky, much of what we see, the glowing arms, the dark rifts, the faint patches of haze, is shaped by these nebulae and clouds. They are the canvas on which the stars are painted, and the paint itself, flowing and reforming across ages. They remind us that the galaxy is not static but alive, not eternal in form but enduring in process. The nebulae are the gentle evidence of change, the soft proof that even the stars are part of a cycle of birth, life, and return. The black hole at the center for most of human history, the center of the Milky Way, was hidden. When people looked up at the night sky, they saw a pale band of stars stretching across the heavens. Toward the constellation of Sagittarius, this band grew brighter, wider, and more crowded with stars. Yet behind this brilliance lay a mystery. The very heart of the galaxy was blocked from view by thick lanes of dust and gas, so dense that no ordinary light could escape them. To the human eye, the galactic center appeared only as a dark rift, a place where the glow of the Milky Way seemed to fade away. It was not until the 20th century, with the rise of radio astronomy, that the veil began to lift. Unlike visible light, radio waves can pass through the dust, revealing sources of energy that had never before been seen. In the early 1970s, astronomers detected a strong and compact source of radio emission coming from deep within Sagittarius. This source was given the name Sagittarius A, and within it, a particularly bright and unusual point was singled out and marked with an asterisk, Sagittarius A. The asterisk indicated that this was no ordinary feature, but something unique. At first, scientists were cautious. The idea of a massive, invisible object at the center of the galaxy seemed extraordinary. Some wondered whether it might be a cluster of stars so dense that individual suns could not be distinguished. Others thought it might be a strange cloud of gas or even an exotic object not yet understood. Yet the intensity of the radio waves and the compactness of their source suggested something far beyond ordinary explanations. As instruments improved, evidence began to accumulate. The region at the center of the galaxy, once invisible, revealed itself as a place of immense activity. Stars moved more quickly there than anywhere else, their orbits suggesting the presence of a hidden mass. The discovery of Sagittarius A was not a single moment, but a gradual unfolding, a process of careful observation, repeated measurements, and slow acceptance. By the end of the century, the idea that a supermassive black hole lay at the heart of the Milky Way had moved from speculation to near certainty. This was the first step in understanding the true nature of the galaxy's core. A discovery not of sight, but of inference, drawn from signals that traveled across space, whispering of something immense and unseen at the very center of our home. After the discovery of Sagittarius A, the next task was to understand what it truly was. The clue lay in the movement of the stars that surrounded it. Astronomers began to track these stars carefully year after year, using the most powerful telescopes available. From Earth, these stars appear faint and distant, yet their motions are surprisingly swift. Some of them trace complete orbits in only a few decades, a brief span in the language of astronomy. These orbits told a clear story. For the stars to move so quickly and so tightly around the galactic center, there had to be something with enormous gravity holding them in place. The size of the orbits, combined with the speed of the stars, revealed the mass of the hidden object. Calculations showed that the center of the Milky Way contained the equivalent of about 4 million suns, all confined within a space no larger than our solar system. No cluster of stars could be so dense without collapsing. No cloud of gas could remain so compact without dispersing. The only explanation that matched the evidence was a supermassive black hole. This conclusion grew stronger as observations improved. In particular, one star, known as S2, became famous. Its orbit carried it very close to Sagittarius A, looping around the invisible center in just 16 years. At its nearest approach, it traveled at speeds of several thousand kilometers per second, faster than almost anything else observed in the galaxy. Its path was a silent confirmation that something immense and compact lay at the core. The presence of this black hole was no longer just a theory. It was a measured fact, grounded in the slow accumulation of data and the precise tracking of stellar paths. The galactic center, once hidden behind dust and mystery, was now revealed as a place where gravity ruled in its most extreme form. Sagittarius A was not only real, but measurable, its mass known, its influence mapped in the quiet orbits of stars that circle endlessly around it. Around Sagittarius A lies a region unlike any other in the Milky Way. It is a place of extremes, where the density of stars, the presence of gas, and the pull of gravity combine to create conditions far more intense than in the quiet reaches of the galactic disk. Close to the center, stars gather in clusters, crowding the space with their light. Some are massive and short-lived, burning brightly and fading quickly. Others are compact remnants, white dwarfs, neutron stars, and perhaps even smaller black holes, circling the supermassive black hole in intricate orbits. Together they form a dense stellar population, the crowded heart of the galaxy. Gas clouds drift through this region as well, pulled and twisted by the gravity of the core. As they move inward, some of the gas is heated to millions of degrees, radiating in X-rays and other high-energy forms of light. These signals reach Earth as faint whispers, but they reveal the restless activity that surrounds the black hole. Magnetic fields thread the gas, bending and shaping it, adding to the turbulence of the environment. Observing this region is not simple. The thick dust of the galaxy lies between us and the center, blocking visible light. To pierce this veil, astronomers rely on radio waves, infrared light, and X-rays, each offering a different view. Infrared reveals the stars. Radio shows the gas streams. X-rays highlight the hottest, most energetic processes. Together, these observations form a layered picture of a place that cannot be seen directly, but whose presence can be traced in many ways. This environment is not quiet, but restless, filled with motions too vast and slow for us to feel, yet ongoing across millennia. It is the hidden machinery of the Milky Way, the crowded stage where gravity, gas, and starlight interact under the silent watch of Sagittarius A. The presence of Sagittarius A is not only a curiosity of astronomy, but also a fundamental part of the Milky Way's structure. At first glance, it might seem strange that a single object, hidden and unseen, could matter so much to a galaxy that spans 100,000 light-years. Yet its role is quiet and steady, influencing the galaxy across billions of years. The gravity of the black hole helps to anchor the central region, keeping the dense cluster of stars bound together. Though its direct pull does not extend across the entire galaxy, the stability it provides near the core shapes the inner structure of the Milky Way. Around it, stars orbit in orderly paths, and gas clouds are guided into the central bulge. Without such a mass at the center, the movements of this crowded region would be less stable, more chaotic, and less enduring. Sagittarius A also plays a role in star formation. Gas that drifts toward the center can be compressed and heated, sometimes forming new stars in bursts of activity. The environment near the black hole is turbulent, but this turbulence can create the very conditions needed for the birth of stars. At the same time, the energy released by infalling gas can push material outward, regulating how much star formation occurs. In this way, the black hole acts both as a source of stimulation and a brake, balancing the processes that shape the heart of the galaxy. Astronomers now believe that nearly all large galaxies contain supermassive black holes at their centers. The Milky Way is not unusual in this regard. Instead, Sagittarius A is one example of a pattern repeated across the universe. Galaxies and their central black holes appear to grow together, influencing one another over time. The presence of Sagittarius A is therefore not an accident but part of the larger design of galaxies, a shared feature of cosmic structure. In this sense, the black hole is not only a detail of the Milky Way but a symbol of what galaxies are. It is a reminder that order can arise from gravity, that structure can persist across billions of years, and that even in silence, immense forces are at work, shaping the places we call home. Although Sagittarius A is known and measured, much about it remains hidden. Unlike the active black holes at the centers of some other galaxies, ours is relatively quiet. Most of the time it lies in shadow, faint and subdued, releasing little energy. Yet every so often, astronomers detect sudden flares, bursts of X-rays or infrared light that rise quickly, glow for a short time, and then fade. These flares may be caused by small clumps of gas falling inward, heating up as they spiral close to the event horizon. They are reminders that even in its silence, the black hole is never entirely still. The event horizon itself is a boundary that we cannot see beyond. Light cannot escape from within it, and so the black hole's interior is forever hidden. What lies there is unknown. General relativity tells us that at the very center lies a singularity, a point where density becomes infinite and the laws of physics break down. But whether this picture is complete, or whether another description will one day take its place, remains uncertain. The black hole is both a fact, grounded in observation, and a mystery, pointing to the limits of our knowledge. There are also questions about its past and future. Did Sagittarius A grow quickly long ago when the galaxy was young and full of gas? Has it consumed stars and smaller black holes in its history? How will it behave when the Milky Way collides with the Andromeda Galaxy billions of years from now? These are questions for which only hints exist. For now, the black hole is quiet, its presence steady, its activity subdued. But across cosmic time, its role may shift, shaping the galaxy in ways we cannot yet foresee. In this way, Sagittarius A is both ordinary and extraordinary. Ordinary because nearly every large galaxy has one. Extraordinary because it is ours, the silent center of our home in the universe, the unseen anchor around which all else revolves. It is a mystery we cannot touch, but also a certainty we can trust, a reminder that even in the quiet heart of the galaxy, great forces move in silence. The history of the Milky Way, the story of the Milky Way begins almost as far back as the universe itself. Astronomers estimate that our galaxy is about 13.5 billion years old, forming not long after the Big Bang, which occurred some 13.8 billion years ago. In those earliest times, the universe was filled with simple elements, mostly hydrogen and helium, spread thinly across expanding space. From this quiet beginning, gravity began its patient work, gathering gas into denser regions, drawing matter together into the seeds of future galaxies. The Milky Way began as one of many such seeds, a collection of smaller protogalaxies slowly merging under their mutual pull. These fragments contained some of the very first stars, known as population 3 stars, which were massive, bright, and short-lived. They produced the first heavy elements through nuclear fusion, and when they ended their lives in supernova explosions, they enriched their surroundings with the materials that would be needed for later generations of stars and planets. Though none of these earliest stars survive today, their influence remains in the chemical traces they left behind. As time passed, the small proto-galaxies combined, forming a larger structure bound by gravity. Dark matter, invisible yet abundant, played a central role in this process. It provided the mass needed to hold the gathering systems together, preventing them from dispersing into space. Without dark matter, the Milky Way could never have taken shape. Instead, with its presence, gas and stars settled into an ever-growing system, the beginnings of the galaxy we now call home. The earliest stages of the Milky Way were chaotic, marked by collisions, bursts of star formation, and shifting shapes. Yet within this chaos lay the foundation of order. Over hundreds of millions of years, the scattered fragments of gas and stars became one. The halo of the galaxy formed, filled with the ancient globular clusters that still orbit today. The bulge at the center began to grow, crowded with stars that have burned for more than 10 billion years. Slowly, the framework of the Milky Way emerged, ready to evolve into the spiral galaxy we now see. As the Milky Way matured, its structure began to change from a collection of scattered fragments into something more ordered. One of the most important steps in this process was the formation of the galactic disk. Over billions of years, the gas within the growing galaxy cooled and settled into a thin, rotating plane. Gravity pulled the material inward, while angular momentum, the tendency of spinning matter to flatten into a disk, shaped it into the broad structure that now defines the Milky Way. This disk became the stage for most of the galaxy's continuing activity. Within it, gas clouds gathered, collapsed, and formed stars. The spiral arms, which appear today as luminous lanes of light, began to take shape as patterns of density moving through the disk. In these arms, gas and dust were compressed, sparking bursts of star formation that lit up the galaxy with clusters of young, bright stars. Over time, the steady rhythm of collapse and renewal filled the disk with billions of suns, each orbiting the galactic center in slow procession. Dark matter again played a quiet but decisive role. Surrounding the galaxy as an invisible halo, it provided the mass to hold the disk together. Without it, the rotation of the Milky Way would have torn the galaxy apart. With it, the spiral arms remained intact, and the disk was able to endure for billions of years. The presence of dark matter explains why the galaxy rotates in the way it does, with stars far from the center moving more quickly than they would if only visible matter were present. By about 8 to 10 billion years ago, the disk was well established. Its thinness gave the Milky Way its distinctive banded appearance when seen from within. From Earth, this band appears as the soft glow of countless stars, blended together across the sky. The disk became the main body of the galaxy, home to most of its stars, and the place where new generations continue to form even now. The building of the disk marked a turning point in the galaxy's history. What began as a chaotic gathering of fragments became an ordered spiral system. The halo and bulge, remnants of the earliest stages, still remain, but the disk is the living heart of the Milky Way, thin, wide, and filled with the quiet motions of billions of stars. The Milky Way did not grow in isolation. Across billions of years, it expanded by drawing in and absorbing smaller galaxies. These mergers were not sudden or violent in the way we might imagine, but slow processes unfolding over hundreds of millions of years. As a smaller galaxy approached, the Milky Way's gravity stretched it apart, pulling its stars into long streams. Some of these stars were scattered into the halo, while others were drawn into the disk or bulge, becoming part of the larger system. Evidence of these mergers can still be seen today. Astronomers have traced faint rivers of stars arcing across the halo, remnants of dwarf galaxies long since absorbed. One of the most studied examples is the Sagittarius dwarf galaxy, which is currently being torn apart by the Milky Way's gravity. Its stars are stretched into a great stream that wraps around the galaxy, a visible reminder that the Milky Way continues to grow by accretion. These mergers enriched the galaxy in several ways. They added new stars, gas, and dark matter, increasing the mass of the Milky Way. They also stirred its structure, shaping the bulge and thickening parts of the disk. Globular clusters, those ancient spheres of stars in the halo, are thought in many cases to have come from smaller galaxies that were captured and consumed. Each merger left behind subtle traces, and by studying the motions and compositions of stars, astronomers can reconstruct the history of these events, piecing together the story of how the Milky Way assembled itself. Though the process sounds destructive, it was also creative. The mixing of gas from different systems fueled new bursts of star formation. The redistribution of stars created the patterns we now see in the halo. The Milky Way we know today is not the product of a single origin, but of many layered together across time. It is a tapestry woven from countless threads, each a galaxy or cluster that once drifted separately, now bound into one. This slow gathering continues even now. Small dwarf galaxies still orbit the Milky Way, some destined to be drawn in and absorbed in the future. The galaxy's history is not finished, but ongoing, part of the steady rhythm of growth and change that has shaped it from the beginning. The Milky Way has not always looked the way it does today. Over billions of years, its structure has evolved, slowly reshaped by the passage of time, the flow of gas, and the orbits of its countless stars. The bulge at the center grew as stars aged and gathered, filling the core with ancient suns. The halo expanded as mergers added new streams of stars and clusters. The disk became thinner and more ordered, its spiral arms maintaining their form even as individual stars within them came and went. The galaxy's chemical composition also changed across time. The earliest stars contained almost nothing but hydrogen and helium. Each new generation, born from the ashes of the ones before, held more heavy elements: carbon, oxygen, iron, forged in stellar cores and spread by supernovae. This gradual enrichment meant that younger stars, like our Sun, contain the materials needed to form rocky planets and, eventually, life. The evolution of the Milky Way is not only a story of structure but also of chemistry, a long transformation of simple beginnings into a system rich with possibilities. The Sun itself has traveled through this evolving galaxy. In its 4.6 billion years of existence, it has orbited the galactic center perhaps 20 times. Along the way, it has passed through spiral arms and quieter interarm regions, its environment shifting with each stage of the journey. Sometimes it may have been near clusters of stars, at other times more isolated. Yet through all these changes, the Sun's orbit has remained steady enough to provide stability for Earth and the life it sustains. The evolution of the Milky Way is measured not in years or centuries, but in billions of years. Entire species may rise and vanish on a single planet during the smallest fraction of its timeline. Civilizations may flourish and fade while the galaxy itself continues, its great arms turning slowly, its stars burning steadily, its structure enduring. To reflect on its evolution is to see time stretched almost beyond comprehension, a reminder of the scale on which galaxies live. The Milky Way is still evolving. Gas continues to flow, stars continue to form, and mergers continue to reshape the halo. Though we see it as a finished system, it is in truth a process ongoing and patient, unfolding across spans of time that far exceed our own. The Milky Way is not unique. Across the universe, billions of galaxies exist, each with its own history of birth, growth, and change. Yet by studying our own, we place it in context, comparing it to others of similar type and age. The Milky Way is a barred spiral galaxy, one of the larger members of its class. It is older than some, younger than others, but in many ways typical of the great spirals that fill the cosmos. Its size, its structure, and even its central black hole reflect patterns repeated again and again across the universe. Within the local group, the Milky Way is one of the two dominant galaxies, the other being Andromeda. Together, they hold most of the mass of the group, drawing smaller galaxies into orbit. Dwarf galaxies circle them both, some destined to merge, others to drift in long, slow arcs. The local group itself is part of an even larger structure, the Virgo supercluster, one among many in the vast web of the universe. Our galaxy is therefore not an isolated island but part of a great network, connected through gravity to systems far beyond our sight. Its history reflects this context. Like other galaxies, the Milky Way grew by absorbing smaller systems. Like others, it built a disk, developed spiral arms, and saw its stars cycle through birth and death. Yet within this typical pattern lies its special meaning. It is the galaxy where the sun formed, where Earth took shape, where life appeared. This context is universal, but its significance is personal. It is both one galaxy among billions and the only one we can call home. The long history of the Milky Way prepares it for the future. Billions of years from now, it will merge with Andromeda, forming a new galaxy that astronomers sometimes call Milkomeda. The stars will continue their orbits, rearranged into a new structure. The black holes at the centers will combine, creating an even greater mass. The Milky Way's individual form will vanish, but its matter, its stars, and its history will live on in the new system. In this way, the Milky Way's history is both complete and incomplete. It stretches back nearly to the beginning of time, and it stretches forward into a future we cannot fully imagine. To place it in context is to see it as one story among many, part of the larger story of the universe itself. A galaxy that is at once ordinary and extraordinary, fleeting in form yet enduring in substance, silent in its motions yet vast in its meaning. The neighbors of the Milky Way does not drift through space alone. Like people in villages or stars in clusters, galaxies too often live in groups, bound together by gravity. Our own galaxy belongs to such a gathering, known simply as the local group. It is not vast compared to the great clusters found elsewhere in the universe, but it is our home cluster, the quiet neighborhood in which the Milky Way resides. The local group contains more than 50 galaxies, most of them small and faint dwarfs. At its heart are three larger members: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. These three define the structure of the group, their gravity holding the smaller galaxies in long orbits. The Milky Way and Andromeda are the giants, each containing hundreds of billions of stars, while Triangulum, though smaller, is still significant compared to the tiny companions scattered around. Gravity binds the local group together. Each galaxy follows its path, but none can escape the pull of the others. Over time, they interact, tugging on one another, altering their motions, and in some cases merging. The smaller galaxies often bear the marks of this influence, stretched into streams or drawn closer to their larger neighbors. The local group as a whole drifts through space, part of an even larger system, but its members remain connected, moving together through the silence of the cosmos. Though modest in scale compared to larger clusters, the local group is still vast by human measures. It stretches across 10 million light-years, a span so wide that even light takes millions of years to cross from one side to the other. Within this space, galaxies shine faintly, their light blending into the larger darkness, each a home to stars, planets, and histories of their own. The local group is our cosmic village, the immediate setting of the Milky Way story. Among all the members of the local group, none is as significant to the Milky Way as the Andromeda Galaxy. It is the nearest large spiral galaxy to us, lying about 2.5 million light-years away. To the unaided eye, it appears as a faint smudge of light in the constellation of Andromeda, visible on clear nights from dark places. With telescopes, its full structure becomes clear. A barred spiral galaxy much like our own, with arms, a bulge, and a halo, stretching more than 200,000 light-years across. Andromeda is larger than the Milky Way, perhaps containing 1 trillion stars. Its mass is comparable, though estimates vary, and together the two galaxies dominate the local group, their combined gravity shaping the orbits of the smaller companions. Where the Milky Way is our home, Andromeda is our great neighbor, a mirror across the void, similar in structure but distinct in its own history. The relationship between the Milky Way and Andromeda is not static. Over time, their mutual gravity has drawn them closer, and they are on a path toward collision. In about 4 to 5 billion years, the two galaxies will meet. The encounter will not be a sudden crash but a slow merging, lasting perhaps billions of years. Stars will rarely collide directly, for the spaces between them are immense, but their orbits will shift, and the shapes of the galaxies will change. The spiral arms will distort, the disks will merge, and in time a new, larger galaxy will form. Astronomers sometimes call this future system Milkomeda. For now, Andromeda remains a quiet neighbor, slowly approaching, its light traveling millions of years to reach us. To look at it is to see both the present and the future, a galaxy shining in its own right, and a partner destined to join with the Milky Way in the long unfolding of cosmic time. Closer than Andromeda and far smaller are two faint companions known as the Large and Small Magellanic Clouds. These are dwarf galaxies that orbit the Milky Way, visible in the southern skies as soft patches of light. For those who live where they can be seen, they have long been familiar, part of the night sky just as much as constellations and stars. To the unaided eye, they look like fragments of the Milky Way itself, small pieces of haze detached from the greater band. The Large Magellanic Cloud, or LMC, is the bigger of the two. It contains several billion stars and stretches across about 14,000 light-years. Within it lies the Tarantula Nebula, one of the most active star-forming regions known, a glowing reminder that even small galaxies can sustain the birth of new stars. The Small Magellanic Cloud, or SMC, is smaller still, a delicate system with perhaps a few 100 million stars. Though modest in size, both clouds are significant, for they interact not only with the Milky Way but also with each other, their mutual gravity shaping their forms and their paths. The orbits of the Magellanic Clouds are complex, influenced by the pull of the Milky Way. Some evidence suggests that they may not have been long-term companions, but rather recent arrivals captured by the galaxy's gravity within the last few billion years. As they move, streams of gas trail behind them, known as the Magellanic Stream. This flow of hydrogen connects the clouds to the Milky Way, feeding our galaxy with fresh material that may one day form new stars. Though small compared to the giants of the local group, the Magellanic Clouds remind us that galaxies live in communities, influencing one another in subtle ways. They are not isolated sparks, but companions in motion, their destinies tied to the larger galaxy they orbit. In the quiet glow of the southern sky, they are both neighbors and participants in the ongoing story of the Milky Way. The Milky Way has more companions than just Andromeda and the Magellanic Clouds. Surrounding it, scattered through the halo, are dozens of dwarf galaxies. These small systems are faint and difficult to see, but they are real neighbors, bound by the gravity of the Milky Way. Some are irregular, their shapes uneven, while others are more spherical, small versions of larger galaxies. Each contains only a few million or a few hundred million stars, a fraction of the numbers found in the great spirals, yet together they form a quiet community around the larger galaxy. One of the most prominent of these is the Sagittarius dwarf galaxy. It is currently being drawn apart by the Milky Way's gravity, stretched into long streams of stars that wrap around the halo. These stellar streams are evidence of the ongoing process of accretion, where smaller galaxies are absorbed into larger ones. They are like threads being woven into the greater fabric, faint but enduring reminders of the Milky Way's ability to gather and grow. Other companions include the Fornax dwarf, the Sculptor dwarf, and many more, each circling in its own slow orbit. Some of these galaxies may eventually merge with the Milky Way, their stars scattering into the disk or halo. Others may remain as satellites for billions of years, small companions quietly moving in the shadows of the larger system. The streams of stars left by these interactions are not only beautiful but also informative. By tracing their paths, astronomers can learn about the Milky Way's mass and shape, for the stars act as test particles, revealing the pull of the galaxy's gravity. These streams are the faint signatures of history written across the night sky, telling of mergers, captures, and the ongoing exchange between galaxies. Though they are small, the dwarf galaxies and the streams they create are important to understanding the Milky Way. They show that even now, the galaxy is not finished, but still in the process of change. The companions that circle it are not separate stories, but part of its larger narrative, linked by the quiet pull of gravity that connects all things. The local group, with its handful of large galaxies and many smaller ones, is itself part of something even greater. Galaxies are not scattered randomly across the universe but arranged in patterns, woven together into a vast web. This structure is sometimes called the cosmic web, a network of filaments and clusters connected by gravity, stretching across hundreds of millions of light-years. The local group belongs to the Virgo supercluster, a broad collection of galaxy groups and clusters bound together on larger scales. The Virgo cluster, a massive concentration of galaxies, lies at the heart of this supercluster, and the local group is one of the smaller branches extending outward. Though the distances are immense, the gravity of the supercluster links these systems, guiding their motions in a quiet and steady flow. From our position within the Milky Way, it is not possible to see this structure directly. Yet by mapping the positions and redshifts of distant galaxies, astronomers have traced the outlines of these filaments, revealing the larger context in which we live. The local group is only one node in this web, one point where threads of galaxies come together. Beyond it lie countless others, each with its own clusters, its own networks, its own histories. To place the Milky Way in this context is to recognize both its smallness and its connection. It is one galaxy among billions, part of a structure so vast that even light takes hundreds of millions of years to cross it. Yet it is not isolated. It is tied by gravity to Andromeda, to the smaller galaxies of the local group, to the Virgo supercluster, and beyond to the web of the cosmos itself. In this way, the Milky Way's neighbors are not only the nearby galaxies that orbit with us but also the distant systems that form the larger whole. Together they make up the fabric of the universe, a structure as intricate as it is immense, in which our galaxy is one thread, shining quietly among countless others. The sun's journey. The sun does not stand still. Though to us it seems fixed in the sky, rising and setting with steady rhythm, it is in fact moving on a much larger scale, circling the center of the Milky Way. This path is shaped by the gravity of the galaxy, just as the Earth's orbit is shaped by the sun. From its place in the Orion Spur, about 27,000 light-years from the core, the sun follows a broad, nearly circular path through the disk of the galaxy. This journey is immense. The sun travels at a speed of more than 800,000 kilometers per hour, yet the distances involved are so great that one orbit takes around 250 million years. Astronomers call this a galactic year. In the entire history of the Earth, with its continents shifting and life evolving, the sun has completed only about 20 of these orbits. Each galactic year marks a cycle of time far greater than anything we know on Earth, a reminder that our solar system is part of motions that extend beyond human scales. The sun's orbit is not flat and featureless. It carries the solar system slightly above and below the plane of the galactic disk in a gentle wave. Over tens of millions of years, the sun rises a little higher, then dips a little lower, weaving its way through the disk. This oscillation adds another rhythm to its journey, a slow, breathing motion through the stars. Despite its speed and distance, the sun's orbit is relatively stable. It does not plunge toward the core or drift outward into the halo. Instead, it follows a steady track, maintained by the balance of gravity and motion. This stability has allowed Earth to exist in a calm region of the galaxy, away from the most crowded and hazardous areas. In this sense, the sun's orbit is more than a path. It is a safeguard, a quiet track through space that has endured for billions of years and will endure for billions more. Over the course of its long life, the sun has traveled many times around the galaxy. In its 4.6 billion years, it has completed roughly 20 full orbits of the Milky Way center. Each orbit has carried it through changing environments, across spiral arms, and through quieter spaces between them. Though these shifts unfold slowly, far beyond the scale of human time, they remind us that the solar system is not fixed but part of the larger rhythm of galactic motion. The spiral arms are regions of greater density, where gas, dust, and stars are more concentrated. As the sun has drifted through them, the night sky above Earth would have looked subtly different, crowded with more bright stars than in the calmer spaces in between. Some astronomers suggest that these passages may have had quiet effects on Earth's history, perhaps altering the flow of comets from the outer solar system or exposing Earth to higher levels of radiation from nearby supernovae. Whether or not these influences shaped life directly, they show that the sun's pathway is not uniform, but a journey through varied regions of the galaxy. In the times between spiral arms, the sun has traveled through quieter zones, where fewer massive stars are born and where supernovae are less common. These periods may have offered stability, with fewer disruptions to the solar system. For billions of years, the alternation between crowded arms and calmer interarm regions has been part of the sun's journey, a slow shifting between denser and more open spaces. The shape of the galaxy itself has also changed during the sun's lifetime. When the sun was young, the Milky Way's spiral arms were not arranged exactly as they are today, and its bulge and halo were still developing. As the galaxy evolved, the sun's orbit carried it through a system that was itself in motion, always shifting and reshaping on the largest scales. In this sense, the past pathways of the sun are part of a greater story, not only of motion but of change, a reminder that both stars and galaxies evolve together across the ages. As the sun has followed its long orbit, it has not traveled in complete isolation. The galaxy is filled with clusters of stars, drifting gas and passing streams, and from time to time the solar system has come near to these companions. These encounters are distant on a human scale, but across millions of years, they form part of the background of the Sun's journey. At times, the solar system may have passed near star clusters, groups of stars bound loosely together. These encounters would not have placed stars in direct danger of colliding with the Sun or its planets, for the distances remain vast, but their gravity may have nudged the far edges of the solar system, where comets lie in a distant reservoir known as the Oort cloud. When disturbed, some of these comets can begin long journeys inward, sometimes reaching the inner planets, a quiet reminder of the galaxy's influence on even the smallest details of life on Earth. The Sun's orbit has also carried it through regions where massive stars once lived and died. In these areas, supernovae have scattered heavy elements into space, enriching the gas and dust of the galaxy. The solar system itself was shaped by such material, for the elements that form the Earth, the iron in its core, the calcium in its rocks, and the oxygen in its air, were created in stars that lived and died before the Sun was born. As the solar system travels, it moves through the legacy of countless earlier stars, drifting through the quiet evidence of their lives and endings. Cosmic rays, high-energy particles that travel across the galaxy, are also part of this environment. Their intensity varies depending on the regions the Sun passes through. At certain times, Earth may have been exposed to slightly higher levels of radiation, subtle influences that weave into the long history of life and climate. These effects are not dramatic, but they remind us that the solar system is never separate from the galaxy, but always part of its wider processes. The encounters and influences of the Sun's path are gentle, unfolding over spans of time so long that they escape ordinary notice. Yet they are real part of the story of how the solar system has moved through the galaxy, quietly shaped by the company of stars and the remnants of their lives. Despite all the motion, the Sun's path through the Milky Way has been remarkably steady. Its orbit is nearly circular, keeping it at a safe and consistent distance from the galactic center. Unlike some stars that drift inward or outward over time, the Sun remains within a broad, stable track, circling the core every 250 million years. This stability has provided Earth with an environment largely free from the most dangerous regions of the galaxy. The Sun's place in the Orion Spur has been especially favorable. This spur is a quieter lane between two of the major spiral arms. It contains fewer of the massive, short-lived stars that end their lives as supernovae, and it avoids the dense crowds of the central bulge. Here, the Sun moves in relative calm, surrounded by ordinary stars much like itself. The distances between them are vast, reducing the chance of disruptive encounters. In this way, the solar system has enjoyed a degree of shelter, a quiet neighborhood within the greater city of the galaxy. This steadiness has been important for the development of life on Earth. A more erratic orbit might have carried the Sun through regions rich in radiation or gravitational disturbances, creating harsher conditions. Instead, the Sun has remained on a path that, while not free from all influence, has allowed stability across billions of years. The long history of Earth's oceans, continents, and living creatures has unfolded against the backdrop of this gentle journey. The Sun's stability is not absolute. It does rise and fall slightly above and below the plane of the galactic disk, in a slow oscillation lasting tens of millions of years. Yet even this motion is modest, never carrying it far from the safety of the midplane. It is a subtle rhythm rather than a disruption, another layer of quiet movement in the Sun's long passage around the galaxy. In the great scale of the Milky Way, the Sun is an ordinary star on an ordinary orbit. Yet for Earth, its steadiness has been extraordinary, providing the conditions for life to flourish in a galaxy filled with extremes. The Sun's journey through the galaxy is far from over. With about 5 billion years of life remaining, it will continue its orbit around the Milky Way many more times. Each orbit will carry it through spiral arms and across calmer stretches, just as it has done in the past. The slow rhythm of its path will continue, marking the passage of galactic years, each lasting hundreds of millions of Earth years. As time moves forward, the Milky Way itself will change. In 4 to 5 billion years, the Andromeda Galaxy will draw near, beginning a long process of merging with the Milky Way. The Sun, by then nearing the later stages of its life, will become part of this encounter. Its orbit will shift as the two galaxies combine, stars scattering into new patterns, spiral arms twisting and dissolving, and the central black holes of both galaxies spiraling together. The Sun will not collide with other stars, for the spaces between them are too vast, but its surroundings will change. The night sky, if Earth still exists, will glow with new and strange shapes as galaxies merge into one. The Sun itself will eventually exhaust its hydrogen fuel. It will swell into a red giant, then shed its outer layers, leaving behind a white dwarf, a dense remnant that will shine faintly for billions of years more. By that time, the Milky Way as we know it will no longer exist. It will have merged with Andromeda, forming a new galaxy that will carry within it the traces of both. The Sun's remnant will continue its orbit, a faint ember in a larger and different system, still circling quietly as part of the cosmic whole. In this way, the Sun's future journey is both certain and unknown. Certain because the rhythms of gravity will continue to carry it forward. Unknown because the exact path it will take depends on the changes of the galaxy itself, changes that stretch far beyond the reach of human prediction. What is sure is that the Sun will remain part of the larger story, bound to the galaxy as it has always been, drifting steadily through the silence of space. Life cycle of stars in the Milky Way. The beginning of a star's life is quiet and hidden. Long before a star shines, it exists as part of a cold cloud of gas and dust, drifting through the Milky Way. These clouds are immense, often spanning dozens or even hundreds of light years. They are made mostly of molecular hydrogen, the simplest and most common element in the universe, along with traces of helium and tiny amounts of heavier elements. Dust grains, made of carbon and silicates, drift within the gas, scattering light and giving the clouds their dark, opaque appearance. Seen from Earth, they often appear as black patches against the background of brighter stars, blocking their light and hiding what lies within. Though they seem still, these clouds are full of slow activity. Gravity works patiently, drawing the gas together. In some regions, a passing shock wave from a supernova or the pressure from nearby hot stars can compress the cloud, tipping the balance so that collapse begins. Once the process starts, small fragments of the cloud break away, each collapsing into its own dense knot. These knots are the seeds of new stars. As collapse continues, the gas grows hotter and denser at the center. A protostar takes shape, surrounded by a disk of material spinning around it. This stage can last millions of years, with the young star still hidden inside its cocoon of gas and dust. From outside, we cannot see the forming star directly, but its presence is revealed through faint infrared light, the heat of its growing core escaping into space. Around the protostar, the disk of gas and dust is busy in its own way. Clumps begin to form, colliding and sticking together, creating larger and larger bodies. In time, these can become planets, moons, asteroids, and comets. Thus, the birth of a star is rarely only the birth of the star itself. It is often the birth of an entire planetary system, each body sharing the same origin within the cloud. The moment that marks the true beginning of a star comes when the core becomes hot enough for nuclear fusion. At about 10 million degrees, hydrogen atoms begin to fuse into helium, releasing energy. This energy pushes outward, balancing the inward pull of gravity. The protostar becomes a main sequence star, shining steadily for the first time. What was once a hidden condensation in a dark cloud is now a visible point of light, one among billions in the galaxy. Stellar nurseries are scattered throughout the Milky Way. They are often found along the spiral arms, where density waves compress the gas into knots, setting off collapse. The Orion Nebula, visible to the eye on a clear winter night, is one of the most famous examples. In its glowing clouds, thousands of young stars are forming, some already visible, others still wrapped in dust. There are larger nurseries too, far more massive and distant, such as the Eagle Nebula or the Carina Nebula, places where clusters of stars are born in great numbers. The process of star birth is not quick, nor is it violent from our perspective. It unfolds over spans of time so long that no single human lifetime can witness its full progression. Yet, in the quiet scales of astronomy, it is a constant process. Even now, new stars are forming in the Milky Way, adding to the population of the galaxy. Each new star continues a cycle that has lasted for billions of years, a cycle that ensures the galaxy is never static but always renewing itself. When we look at the night sky, it is easy to see only the stars already shining. But behind them, hidden in darkness, are countless stars still waiting to emerge. They lie in their cradles of dust and gas, silent and unseen, until gravity and time bring them forth. The story of stellar nurseries is the story of beginnings, quiet, gradual, and steady, the patient unfolding of light from darkness when a star emerges from its nursery and begins nuclear fusion in its core. It enters the stage known as the main sequence. This is the long, steady period of its life, when it shines with the greatest stability. For most stars, the main sequence will last for the majority of their existence, sometimes stretching across billions of years. During this time, hydrogen in the core is steadily converted into helium, releasing energy in the form of light and heat. It is this quiet and balanced process that allows a star to shine so consistently. The main sequence is not the same for all stars. A star's mass, the amount of material it contains, determines its path. The smallest stars, known as red dwarfs, contain only a fraction of the sun's mass. They burn their hydrogen slowly, producing a faint light that is difficult to see without telescopes. Yet their very faintness gives them extraordinary longevity. While the universe itself is about 13.8 billion years old, some red dwarfs are expected to live for trillions of years, far longer than the cosmos has yet existed. They will be the last lights to fade, glowing dimly in a distant future when other stars have long since died. Stars of medium mass, like our Sun, follow a different path. The Sun has been on the main sequence for about 4.6 billion years and is expected to remain there for another 5 billion years. It shines with steady light, providing the energy that sustains life on Earth. Its hydrogen burns at a moderate pace, not too fast to shorten its lifespan, and not too slow to leave it faint and unnoticed. This balance makes stars like the Sun important to galaxies, for they provide long-term stability and illumination. The most massive stars live very differently. Blue giants and supergiants may contain dozens of times the Sun's mass. They burn through their hydrogen at an astonishing rate, shining millions of times brighter than the sun but exhausting their fuel in only a few million years. To the galaxy, these stars are brief but brilliant, flooding their surroundings with radiation, shaping gas clouds with their energy, and eventually enriching the interstellar medium when they end their lives in supernova explosions. Their role is not to endure but to transform, influencing the regions around them in their short lifetimes. The diversity of main sequence stars gives the Milky Way its texture. In the spiral arms, clusters of young, massive stars shine brightly, giving the arms their bluish glow. In the quieter regions, red dwarfs dominate, countless faint lights that form the background of the galaxy's population. Medium stars, like the sun, are scattered everywhere, modest in brightness but steady in presence. Together, these stars form the steady backdrop against which the more dramatic processes of stellar birth and death take place. Life on Earth is possible only because of the sun's main sequence stability. For billions of years, its light has been steady, neither flaring wildly nor fading quickly. This consistency has allowed oceans to form, climates to stabilize, and life to evolve. If the sun were larger and shorter-lived, there would not have been time for life to take hold. If it were smaller and cooler, Earth might never have warmed enough to sustain it. The sun's place on the main sequence is therefore not only a fact of astronomy but also a condition of our existence. In the galaxy, main sequence stars are the quiet workers, carrying out their task of shining steadily across unimaginable spans of time. They are not rare events or fleeting displays, but the normal state of starlight. To gaze at the Milky Way is to see countless stars on this journey, each one burning its hydrogen into helium, each one adding to the soft glow of the galaxy. They are the constant rhythm of the cosmos, a reminder that even in a universe of change, there are phases of stability that last for ages. Every star eventually changes. When the hydrogen in its core begins to run low, the long stability of the main sequence gives way to a new and more dramatic phase of life. For many stars, including our Sun, this transition leads to the stage of becoming a giant. The changes are slow on a human scale but swift in the life of a star, measured in millions rather than billions of years. In a star like the Sun, when hydrogen in the core is mostly exhausted, fusion slows. Without the steady outward pressure of nuclear reactions, gravity pulls inward, compressing the core. As the core shrinks, it grows hotter, igniting fusion in a surrounding shell of hydrogen. This change forces the outer layers of the star to expand outward. The star swells to many times its original size, and its surface cools, giving it a reddish hue. It becomes a red giant, far larger but cooler in color than before. In this state, a star that was once modest like the Sun can grow so large that it would engulf the orbits of its innermost planets. For more massive stars, the transformation is even greater. Stars many times the mass of the Sun can become supergiants, expanding to hundreds or even 1,000 times their original size. Some of these stars burn with a blue-white brilliance, their cores so hot that heavier elements like carbon and oxygen begin to fuse. Others swell into red supergiants, their surfaces cooler but their size immense, glowing as vast orbs in the night sky. Betelgeuse in the constellation Orion is one of the nearest examples, a red supergiant visible even to the naked eye. Its size is so great that if placed at the center of our solar system, it would extend beyond the orbit of Mars. The appearance of a star during its giant phase is striking, but its stability is short-lived compared to the main sequence. Giants are stars in transition, moving through stages of nuclear fusion as their cores change. In low and medium stars, helium fusion begins after the hydrogen shell burns out, producing carbon and oxygen. In massive stars, heavier and heavier elements ignite in sequence: neon, silicon, iron. Each stage shorter than the last, each step bringing the star closer to its end. Despite the drama of these changes, the giant phase is an ordinary part of stellar evolution, repeated countless times across the galaxy. Many of the brightest stars in the night sky are giants or supergiants, standing out because of their size and luminosity. Their brilliance often hides their brevity, for they represent only a small fraction of a star's lifespan. Where red dwarfs can endure for trillions of years, a blue supergiant may shine in this phase for only a few million years before its death. The swelling of giants also has consequences for their surroundings. As stars expand, their outer layers can become loosely bound, drifting outward into space. Stellar winds carry gas and dust away, enriching the interstellar medium with material that will one day form new stars and planets. In this way, the giant phase is not only an ending but also a contribution, part of the cycle that recycles material within the galaxy. The Sun itself will one day follow this path. In about 5 billion years, it will leave the main sequence and expand into a red giant. Its light will grow brighter, its outer layers will swell, and Earth, if it still exists, will be transformed by the heat. Eventually, the Sun will shed its outer layers entirely, leaving behind only its core. For now, though, it remains steady on the main sequence, but the giant phase awaits in its distant future. To look at giants and supergiants is to glimpse stars caught between stability and conclusion. They are immense, luminous, and short-lived, filling the galaxy with bursts of brilliance that contrast with the faint endurance of dwarfs. Together, they add variety to the stellar population, showing that stars, like all things, have stages, beginnings, middles, and ends, each one contributing to the larger rhythm of the Milky Way. Every star, no matter its size, eventually reaches an end. The manner of its death depends on its mass, but the conclusion is always the same. The steady rhythm of nuclear fusion cannot last forever. When the fuel runs out, the balance between gravity pulling inward and pressure pushing outward is broken, and the star enters its final stage. Though these endings vary in detail, they are all part of the ongoing cycle of matter within the galaxy. For stars like the Sun, which are of moderate mass, the end is quiet. After spending billions of years on the main sequence, such stars expand into red giants. In this swollen form, they shed their outer layers into space, releasing gas and dust in gentle flows. What remains at the core is compressed into a white dwarf, a dense remnant about the size of Earth, but with the mass of the Sun, white dwarfs no longer produce energy through fusion, but they still glow faintly with leftover heat. Over billions of years, they slowly cool and fade, becoming dark and invisible. This quiet transition is the fate of most stars in the Milky Way. For more massive stars, the ending is far less gentle. When their fuel is exhausted, their cores collapse under the force of gravity. The collapse happens so quickly and with such force that the outer layers rebound outward in a vast explosion known as a supernova. In a moment, the star releases more energy than the Sun will produce in its entire lifetime. The explosion scatters heavy elements, carbon, oxygen, iron, gold into space, enriching the galaxy. These elements become part of future clouds, forming new stars, planets, and eventually the building blocks of life. Supernovae are rare on human timescales, but across the galaxy, they are common enough to continually replenish its matter. The remnants of these massive stars can take two forms: If the collapsing core is between about 1 and 3 times the mass of the Sun, it becomes a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Neutron stars are small, only about 20 kilometers across, but their gravity and density are extreme. Some spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. These are known as pulsars, and they can be detected from Earth as regular signals, steady and precise. If the core is more massive still, the collapse does not stop. Gravity overwhelms every other force, compressing the matter into a black hole. In this case, the star leaves behind no visible remnant, only a region of space where gravity is so strong that not even light can escape. The star has ended, but its presence continues in the form of an unseen mass, bending space and drawing in anything that comes too near. Not all deaths are sudden or explosive. Some low-mass stars, like red dwarfs, burn so slowly that they never reach the giant phase in the lifetime of the universe. Instead, they simply fade over trillions of years, their light dimming until they vanish. None have yet reached this point, for the universe is still too young. But in the far future, the quiet fading of countless red dwarfs will be the dominant story of the galaxy. Though the death of a star marks an ending, it is also a beginning. The material returned to space through stellar winds, planetary nebulae, and supernovae becomes part of the interstellar medium, the reservoir from which new stars are born. In this way, the end of one star directly contributes to the birth of another. The cycle is unbroken, repeating endlessly across the galaxy. To reflect on the death of stars is to see not only finality but renewal. Each fading white dwarf, each cooling remnant, each supernova and black hole is part of a process that ensures the galaxy continues to evolve. The light of today's stars shines because of the deaths of those that came before. The stars we see are both present and past, evidence of endings and beginnings woven together in the long story of the Milky Way. The death of stars does not end their story. In the Milky Way, the matter that once formed the bodies of stars is never wasted. It is returned to the galaxy, dispersed into space, and gathered again into new clouds. From these clouds, new stars and planets are born. This ongoing process of recycling and renewal gives the galaxy its life, keeping it from becoming static, ensuring that its light is continually refreshed. When a star like the Sun ends its life, it sheds its outer layers as a planetary nebula. The gases drift outward, mixing with the interstellar medium. These gases include not only hydrogen and helium, but also heavier elements such as carbon and oxygen, produced in the star's core. In massive stars, the enrichment is even greater. When they explode as supernovae, they scatter iron, nickel, silicon, and even trace amounts of gold and uranium into space. These elements are carried far across the galaxy, joining with existing clouds of gas and dust. Over time, gravity gathers these enriched materials into molecular clouds, the nurseries of future stars. Within these clouds, new generations begin their lives, inheriting the elements of the stars that came before. Planets form from the leftover material, their rocks and atmospheres containing the same atoms forged in ancient stellar cores. On Earth, every atom of calcium in bones, every atom of iron in blood, and every atom of oxygen in the air was once part of a star. The cycle of recycling is not abstract, but immediate and personal, linking human life to the history of the galaxy. This cycle also explains why stars born later in the galaxy's history contain more heavy elements than the earliest stars. The first stars formed almost entirely from hydrogen and helium, with no heavier elements to begin with. Today, however, stars are born from gas that has been enriched for billions of years. The Sun, for example, contains about 2% heavier elements, a small fraction but enough to allow the formation of rocky planets like Earth. Without the recycling of earlier generations, our solar system could not exist in its present form. The process of renewal is not uniform. Some regions of the galaxy are richer in heavy elements, while others remain poor. Spiral arms, where star formation is most active, are continually replenished, while the halo remains older and less enriched. Yet across the galaxy as a whole, the cycle ensures a slow but steady increase in complexity, a quiet growth in the richness of the material available for new worlds. Even in death, stars influence the galaxy's structure. The energy of supernova explosions stirs the interstellar medium, compressing nearby clouds and sometimes triggering the birth of new stars. Stellar winds from giants carve out cavities, shaping the regions where later generations will form. These processes are subtle on short timescales, but over millions of years, they sculpt the galaxy, passing along the influence of one generation to the next. In this sense, the Milky Way is not just a collection of stars, but a living system, constantly renewing itself. The cycle of birth, life, death, and renewal is what keeps it active, what ensures that light continues to shine. Without recycling, the galaxy would eventually run out of gas, its stars fading one by one until only remnants remained. With recycling, it remains dynamic, its story ongoing, its light ever replenished. To consider this cycle is to see continuity in change. The stars we see tonight carry within them the ashes of stars that lived long before Earth was formed. The atoms of our own bodies were shaped in ancient explosions, scattered into space, and gathered again into the cloud that gave birth to the sun. The cycle of recycling and renewal is not only the story of the Milky Way but also the story of our own origins, a quiet reminder that we are part of the galaxy's long history. Dark matter and the galaxy. When astronomers first began to measure the motions of galaxies in detail, they noticed something puzzling. The stars and galaxies, including those in the Milky Way, were moving in ways that did not match the amount of visible matter. In a system governed only by the gravity of the stars and gas we can see, stars farther from the center should orbit more slowly, just as planets farther from the sun move more slowly. Instead, astronomers found that the stars at the edges of galaxies moved just as quickly as those nearer the center. The expected drop in orbital speed never came. This discrepancy suggested that something else was present, something invisible, adding to the mass of galaxies and holding their stars in faster orbits. Without it, the outer stars should have drifted away into space. With it, the galaxies remained intact. The evidence was so striking that it required a new way of thinking. Astronomers concluded that galaxies must contain large amounts of unseen matter, outweighing the stars and gas that were visible. The idea of dark matter began to take form in the early 20th century. In the 1930s, the Swiss astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving too quickly to be bound by the visible matter alone. He proposed that there must be dunkle materie, dark matter, holding the cluster together. At the time, the idea was met with uncertainty, for the evidence was limited and the nature of this matter was unknown. Decades later, stronger proof emerged from the careful work of astronomers studying spiral galaxies. Vera Rubin, working in the 1970s, measured the rotation curves of galaxies with great precision. Instead of falling off at the edges, the curves remained flat, showing that stars far from the center orbited just as fast as those near it. This could not be explained by visible matter alone. Rubin's results confirmed that the majority of a galaxy's mass must be invisible, present in a vast, unseen halo surrounding the disk. The discovery was profound. It revealed that what we see, the stars, the nebulae, the glowing spiral arms, is only a small fraction of what actually makes up a galaxy. Most of its substance is hidden, detectable only through its gravitational influence. The stars are like lights floating in an ocean of invisible matter, guided and held by its unseen weight. For the Milky Way, the same pattern applies. When astronomers measure the motions of stars and gas in our galaxy, they too find that the outer regions move more quickly than they should if only visible matter were present. The conclusion is unavoidable. Our galaxy, like all others, is immersed in a vast halo of dark matter. Though we cannot see it, we know it is there, shaping the structure and stability of the system we call home. The discovery of dark matter was not a sudden revelation but a slow accumulation of evidence. Each measurement, each rotation curve, each cluster observed added to the picture. Over time, the case became undeniable. Something unseen makes up the majority of the universe's mass. What it is, no one yet knows, but its presence is certain, written in the motions of galaxies themselves. To consider dark matter is to recognize the limits of sight. The universe is not only what we can see, but also what we can infer from the way things move. The stars tell us, by their orbits, that a hidden mass surrounds them. The galaxies tell us, by their motions, that they are bound by something greater than their visible parts. The discovery of the invisible is a reminder that the cosmos is deeper than appearances, and that much of its substance lies beyond the reach of light. The Milky Way itself carries the same signature of dark matter that has been observed in other galaxies. When astronomers measure the motions of stars and clouds of gas within our galaxy, they find that the speeds do not match the gravity of visible matter alone. This pattern is not subtle but clear, showing that most of the galaxy's mass is invisible. The stars and nebulae we see are only a thin layer resting within a much larger halo of unseen substance. In the disk of the Milky Way, stars orbit the galactic center much as planets orbit the sun. According to ordinary expectations, the farther a star lies from the center, the more slowly it should move, because the visible mass drops away with distance. Yet observations show something different. Stars in the outer disk, tens of thousands of light-years from the center, orbit almost as quickly as stars near the middle. The rotation curve of the Milky Way, when plotted, remains flat rather than falling off. This is the strongest evidence that the galaxy is immersed in a halo of dark matter, extending far beyond the visible spiral arms. The halo is vast, stretching well past the outermost stars and dwarf galaxies bound to the Milky Way. It may extend for hundreds of thousands of light-years, shaping the motions of objects across the space. Globular clusters, those ancient groups of stars in the halo, move under its influence, their paths tracing out the hidden gravity. Streams of stars left behind by merging dwarf galaxies also reveal the same pattern. Their shapes, stretched and bent, reflect the pull of dark matter, which guides their motions even though it cannot be seen. Gas clouds provide another line of evidence. The Milky Way contains enormous reservoirs of hydrogen gas, spread throughout the disk and halo. By measuring how these clouds move, astronomers find that their velocities also require far more mass than is visible. The unseen halo appears again, its gravity silently holding the system together. Without it, the gas and stars at the edges of the galaxy would not remain bound. Even the way satellites orbit the Milky Way speaks of dark matter. the Magellanic Clouds, the Sagittarius Dwarf Galaxy, and many other small companions are all influenced by the unseen halo. Their orbits, sometimes stretching across millions of years, are shaped not only by the stars of the Milky Way but by the vast envelope of invisible matter surrounding them. The evidence does not come from a single measurement, but from many sources, all pointing in the same direction. The rotation of the disk, the motions of globular clusters, the paths of stellar streams, the velocities of gas clouds, and the orbits of satellite galaxies all reveal the same truth. The Milky Way is far more massive than its visible matter suggests. The stars and nebulae we see make up only a small fraction of the total. The rest, perhaps more than 80%, lies in the form of dark matter. To picture the Milky Way without dark matter is to imagine a system that could not exist in its current form. The spiral arms would not hold together. The outer stars would fly off into space. The galaxy itself would be unstable. Yet with dark matter, the motions become understandable. Its hidden mass provides the glue that binds the system, the framework that allows the visible parts to remain in place. In this way, the Milky Way becomes a quiet demonstration of the unseen. Every orbit, every path, every stream of stars tells the same story. What we see is not all that is there. The galaxy is immersed in an invisible halo, vast and enduring, shaping its form and stability. It is a presence we cannot touch or see, but one that surrounds us always, part of the very structure of the home we live in. Though the evidence for dark matter is strong, its nature remains one of the greatest mysteries of modern science. Astronomers and physicists agree that it must exist, for its gravitational influence is clear, but what it is made of has not yet been discovered. Unlike stars, gas, or dust, dark matter does not emit or absorb light, cannot be seen through telescopes. Its presence is known only through its effects on the motions of galaxies and clusters, and through the way it bends light from distant objects by gravity. Beyond these clues, its identity remains hidden. One of the main ideas is that dark matter could be made of particles that interact only weakly with ordinary matter. These are sometimes called WIMPs, weakly interacting massive particles. If they exist, they would be far more numerous than ordinary atoms, yet almost impossible to detect because they rarely collide with other particles. Experiments deep underground and in space have been designed to search for them, but so far, no direct detection has been confirmed. The search continues, with new detectors being built to increase sensitivity, waiting for even the faintest signal of a passing particle. Another possibility is that dark matter could consist of objects known as machos, massive compact halo objects. These would be things like faint stars, brown dwarfs, or even black holes, spread throughout the galactic halo. While some of these objects certainly exist, they cannot account for all of the dark matter, because the amount of mass they provide is not nearly enough. Observations using gravitational lensing, where the light of distant stars is bent by hidden masses, suggest that machos make up only a small portion of the unseen matter. Some theories explore even stranger possibilities. Perhaps dark matter is made of axions, hypothetical particles predicted by certain extensions of physics. Or perhaps it consists of primordial black holes, formed in the very early universe, long before stars or galaxies. These ideas remain speculative, but they show the wide range of possibilities being considered. Each carries challenges of detection and explanation, and none has yet been proven. What makes dark matter especially mysterious is that it does not fit neatly into the familiar categories of physics. Ordinary matter interacts through electromagnetism, which produces light and heat, yet dark matter does not. It also seems not to interact strongly with itself, for it does not clump together in the way gas does. Instead, it forms smooth, extended halos around galaxies, shaping them without being seen. Its silence makes it elusive, yet its presence is undeniable. The Milky Way is one laboratory where its influence is felt daily. Every orbit of a star in the disk, every path of a globular cluster in the halo, every stream of stars pulled from merging dwarfs testifies to the presence of dark matter. Yet none of these observations tells us exactly what it is. We can measure its effects but not touch its substance. It remains a framework without a face, a necessary element in our equations, but not yet in our grasp. The mystery of dark matter extends beyond astronomy into philosophy. It reminds us that the universe is not fully known, that most of its content lies outside human senses. What we call visible matter is only a minority of reality, perhaps less than 20%. The rest is unseen, not because it does not exist, but because it does not shine. To live in the Milky Way is to live within this larger presence, carried by it, surrounded by it, dependent on it for the galaxy's very structure. Though the search continues, it may be many years before the true nature of dark matter is revealed. New instruments, new experiments, and new theories will be needed. Until then, it remains both a certainty and a mystery, a presence that shapes our galaxy while keeping its identity hidden. Dark matter is not only an unseen mass that fills the galaxy. It is also the foundation upon which the Milky Way exists. Without it, the galaxy would not have formed in the way it did, nor would it remain as stable as it is today. Though we cannot see it, dark matter provides the framework that shapes the galaxy, quietly guiding its structure and ensuring its endurance across billions of years. The earliest role of dark matter began at the dawn of the universe. After the Big Bang, ordinary matter, hydrogen, helium, and a trace of lithium, was too hot and energetic to clump together on its own. Dark matter, unaffected by light or radiation, was able to begin gathering much earlier. It formed invisible scaffolds, clumps and filaments of mass that ordinary gas later fell into. These scaffolds became the seeds of galaxies, including the Milky Way. Without dark matter, the gas would have remained too diffuse, and galaxies might never have condensed into being. In this sense, dark matter is not an afterthought but a cause. The Milky Way exists because dark matter provided the initial structure for its birth. In the present galaxy, dark matter continues to play its role. The halo of unseen mass extends far beyond the disk of stars, enveloping the Milky Way in a sphere of gravity. This halo ensures that the outer stars and gas remain bound, preventing them from drifting away. It also helps to keep the spiral arms intact, for the additional gravity strengthens the overall structure of the disk. Without dark matter, the stars at the edge of the galaxy would orbit too quickly to remain attached, and the Milky Way would slowly fly apart. Instead, the galaxy remains stable, its graceful spiral arms turning steadily for billions of years. Dark matter also shapes the paths of smaller galaxies that orbit the Milky Way. The Magellanic Clouds, the Sagittarius Dwarf, and many others move not only under the pull of visible stars but also under the weight of the dark halo. Their orbits, often stretching across millions of years, are dictated by this unseen mass. Streams of stars drawn from them trace the contours of the halo, showing that dark matter is not only a background presence but an active part of the system's dynamics. On a smaller scale, dark matter influences the conditions in which stars form. By holding gas within the galaxy, it ensures that clouds of hydrogen remain available to collapse into new stars. Without the extra gravity, much of this gas might have escaped into intergalactic space. The long history of star formation in the Milky Way, from its first generations to the present, has been made possible by the retention of gas within the gravitational well created largely by dark matter. The role of dark matter is therefore quiet but fundamental. It does not shine. It does not burn. It does not form planets or stars. Yet it provides the framework that allows all of these things to exist. The visible Milky Way, with its glowing arms, its clusters, its nebulae, and its billions of suns, is like a delicate fabric stretched across an invisible frame. Remove the frame and the fabric would unravel. Keep it in place, and the pattern remains, turning steadily through time. When we look at the Milky Way in the night sky, we see only the luminous part of this system. Behind it, unseen but essential, lies the dark matter halo, holding it all together. The stars shine brightly, but it is the unseen mass that ensures their dance continues. The role of dark matter in the galaxy is not spectacular but sustaining, not visible but vital, a silent partner in the story of the Milky Way. The Milky Way is only one galaxy among billions, yet the mystery of dark matter extends far beyond it. Everywhere astronomers look, they find the same signs. Galaxies rotating too quickly for their visible mass, clusters of galaxies bound together more tightly than their stars and gas should allow, and light from distant objects bent in ways that reveal hidden mass. The evidence is universal. Dark matter is not unique to our galaxy, but a feature of the cosmos as a whole. On the largest scales, dark matter shapes the structure of the universe. After the Big Bang, it gathered into filaments and clumps, forming the scaffolding of the cosmic web. Ordinary matter flowed into these invisible structures, cooling and condensing into the galaxies we see today. Without dark matter, the universe would not have organized itself into galaxies, clusters, and superclusters. Instead, it might have remained diffuse, with stars forming only in small, scattered groups. The presence of dark matter explains why the universe has the structure we observe. Vast networks of galaxies connected across space, with great voids lying between them. Galaxy clusters provide some of the strongest evidence for dark matter. These are enormous collections of hundreds or thousands of galaxies, bound together by gravity. When astronomers measure the motions of galaxies within a cluster, they find that there is far too little visible matter to hold them together. The hot gas between the galaxies also points to the same conclusion. It glows in X-rays, yet it would escape the cluster unless a hidden mass kept it bound. Dark matter provides the explanation, outweighing the visible matter many times over. Gravitational lensing, predicted by Einstein's theory of general relativity, offers another line of proof. When light from a distant galaxy passes near a massive object, it is bent, creating arcs or multiple images. Astronomers studying clusters of galaxies find lensing effects far stronger than could be explained by visible matter alone. The unseen mass of dark matter is required to explain the bending of light. In this way, the cosmos itself reveals the hidden presence of matter that cannot be seen directly. In the Milky Way, dark matter plays the role of a local framework. In the universe as a whole, it plays the role of a universal foundation. Current estimates suggest that dark matter makes up about 27% of the total content of the universe, while ordinary matter, the stars, planets, gas, and dust, accounts for less than 5%. The rest, about 68%, is something even stranger: dark energy, a force driving the expansion of the universe to accelerate. In this balance, ordinary matter is the minority. Most of the universe is invisible, composed of dark matter and dark energy, both poorly understood but undeniably present. The larger picture is one of humility. What we see when we look at the stars is only a fraction of what exists. The bright spiral arms of the Milky Way, the glowing clusters of distant galaxies, and even the light of the most brilliant supernovae are small compared to the vastness of the unseen. The visible universe is like a thin surface layer, while the deeper structure lies in the invisible mass and energy that fill space. Though its nature remains unknown, dark matter has already reshaped our understanding of the cosmos. It tells us that sight alone is not enough, that the universe must be measured not only by light but also by motion, by gravity, by the bending of space itself. In this way, dark matter serves as a reminder of the limits of perception and the depth of mystery that still surrounds us. The Milky Way, with its unseen halo, is one example among countless others. Across the universe, every galaxy carries the same hidden framework, each one turning steadily within its invisible mass. To reflect on the larger picture is to see the Milky Way not as an isolated case but as part of a universal pattern, a galaxy shaped by the same unseen presence that guides them all. The Milky Way is a barred spiral galaxy, and one of its defining features is its spiral arms. These arms are the broad, curving lanes of stars, gas, and dust that wind outward from the central bar, stretching across the disk in graceful arcs. They are not sharp or rigid lines, but vast regions where the density of matter is higher than in the surrounding spaces. From our position within the disk, we cannot see the arms in their full sweep. Instead, we see them as glowing bands, rich in clusters and nebulae, scattered across the night sky. Yet through careful mapping, astronomers have revealed their general structure, showing the Milky Way to be a system with multiple arms radiating from its core. Among the major arms, the Perseus arm is one of the most prominent. It lies beyond the Sun's orbit, sweeping outward into the outer regions of the galaxy. It is a long, bright lane filled with star-forming regions, glowing nebulae, and clusters of young stars. Parallel to it lies the Scutum Centaurus arm, another of the great structures, which extends from the near side of the bar and curves far into the outer disk. Together, these arms form the broad framework of the galaxy's spiral structure. Closer to the galactic center lies the Sagittarius arm. This arm is rich in star-forming activity, containing some of the most famous nebulae and clusters visible from Earth. It is one of the inner arms, winding tightly around the core, and serves as a bridge between the bar and the outer spiral structure. Within it, bright young stars and glowing gas clouds testify to the ongoing rhythm of stellar birth. The Sun itself does not lie in one of the great arms but in a smaller branch, sometimes called a spur. This is the Orion spur, located between the Sagittarius arm and the Perseus arm. It is a modest feature compared to the great arcs of the galaxy, but for us it is home. The Orion spur contains the Sun, the Earth, and the familiar stars of the constellations visible in the night sky. It is from this vantage point that humanity has observed the heavens, mapping the larger structure from within. Beyond these, the Milky Way also contains other arm-like features. Some are smaller branches or spurs that extend from the main arms, connecting or curving into the disk. These features show that the spiral structure is not a simple pattern but a complex system of curves, overlaps, and extensions. The arms are not identical, nor perfectly symmetrical, but varied in length, width, and brightness. The spiral arms define the appearance of the galaxy, giving it the structure we imagine when we think of a barred spiral. They are not isolated entities but part of the continuous disk, where stars orbit the center in vast numbers. Within the arms, the density of stars and gas is higher, making them appear as glowing lanes when viewed from afar. Between the arms, the density is lower, but still filled with stars, showing that the arms are enhancements rather than strict boundaries. From Earth, our view is limited by our position within the disk and the dust that blocks much of our sight. We see the arms as sections, revealed by bright nebulae and clusters, rather than as sweeping curves. Yet by combining radio observations of hydrogen gas, measurements of stellar distances, and mapping of star-forming regions, astronomers have pieced together the overall layout. The picture that emerges is one of a galaxy with multiple arms, linked to a central bar, and extending outward in arcs that define the Milky Way's form. The structure of the spiral arms is both a detail and a foundation. It is a detail because it is only one aspect of the galaxy's overall form. It is a foundation because it shapes where stars form, how gas flows, and how the galaxy appears when seen as a whole. To understand the arms is to see the Milky Way not as a random scattering of stars, but as a patterned system, organized and graceful, turning slowly through time. At first glance, spiral arms may seem like permanent structures, as if they were solid lanes of stars stretching outward from the center of the galaxy. In truth, they are not fixed at all. They are patterns, regions where matter is more concentrated, but not objects in themselves. Stars move in and out of the arms as they orbit the galaxy, showing that the arms are not rigid features, but shifting density waves flowing through the disk. The idea of spiral arms as density waves was developed in the 20th century, when astronomers studied how galaxies maintained their spiral shapes. Without such a process, the arms would quickly wind too tightly as the stars rotated at different speeds, and the pattern would vanish. Instead, galaxies like the Milky Way retain their spiral form for billions of years. The solution was that the arms are not made of the same stars all the time, but are instead areas where stars and gas are temporarily crowded together. As stars move along their orbits, they enter an arm, linger in the denser region, and then pass out of it again, much like cars moving through a traffic jam. In this sense, the arms are patterns of higher density moving through the galaxy, not permanent features. Stars of all ages can be found in them, but young stars are especially visible there because the dense gas clouds within the arms are where new stars are born. The arms glow with bright, massive stars that formed recently, and with nebulae illuminated by their light. These features give the arms their luminous appearance, while the older stars pass through more quietly, adding to the background population. Gas clouds also respond strongly to the density waves. When a cloud of hydrogen enters an arm, the higher pressure within the wave compresses it, sometimes triggering collapse and star formation. This is why the arms are rich with stellar nurseries, bright with new clusters and glowing nebulae. The density waves act like a gentle but steady influence, encouraging the galaxy to continue forming stars where the conditions are right. Because the arms are patterns rather than rigid objects, their shapes can change over time. Some galaxies show two grand arms, sweeping cleanly from the center. Others, including the Milky Way, show multiple arms with branches, spurs, and irregular features. The exact pattern depends on the history of the galaxy, its mass, its rotation, and its interactions with companions. Even within the Milky Way, astronomers continue to refine their maps, finding new details of the arm's structure and extent. This shifting and pattern-like nature can be difficult to imagine from within. From Earth, we see the arms only as bands of stars and nebulae, stretching across the night sky. We cannot see the larger sweep, the slow movement of density waves, or the way stars flow in and out of them. Yet through careful observation and theory, The arms can be understood not as permanent highways of stars, but as rhythmic waves passing through the disk, guiding the flow of matter and light. The nature of spiral patterns also shows how the galaxy is both stable and dynamic. Stable because the arms persist for billions of years, giving the Milky Way its familiar form. Dynamic because the individual stars within the arms are always changing, moving, and passing through. What looks from afar like a fixed structure is in truth a flowing pattern, maintained not by permanence but by rhythm. To see spiral arms in this way is to understand them not as things but as processes. They are the galaxy's way of organizing its matter, of sustaining star formation, of shaping its visible form. They are not solid but shifting, not rigid but flowing, not static but alive with movement. The arms of the Milky Way, like those of other spiral galaxies, are patterns of density written into the great disk, a dance of stars and gas that endures across the ages. The spiral arms of the Milky Way are not empty lanes of stars but active regions where much of the galaxy's life unfolds. Within these arms, gas clouds are compressed, new stars are born, and clusters shine brightly against the background of older stars. They are places of activity within the otherwise quiet flow of the galactic disk, glowing with the combined light of countless suns and nebulae. The density waves that form the arms encourage star formation. As clouds of gas drift into an arm, they are gently compressed, increasing their density until gravity can take over. The result is the collapse of molecular clouds into stellar nurseries, places where thousands of stars may be born at once. Many of these stars are small and faint, destined to shine for trillions of years, but some are massive and short-lived, flooding their surroundings with light and energy. These young, massive stars give the arms their distinctive brilliance. Their blue-white light stands out, making the arms appear as glowing structures when viewed from afar. Nebulae are another hallmark of the spiral arms. These vast clouds of gas and dust are often illuminated by the hot, young stars within them, producing glowing regions that mark sites of recent star formation. Examples in our galaxy include the Orion Nebula, the Lagoon Nebula, and the Eagle Nebula, all located in or near spiral arms. Their soft glow and intricate shapes reveal the constant renewal of the galaxy, as one generation of stars gives way to the next. Clusters of stars also gather in the arms. Open clusters, loose groups of young stars, often form together from a single cloud. Over time, they drift apart, their members spreading across the disk. But while they are young, they mark the spiral arms with points of brightness. Some of these clusters are visible even to the naked eye, such as the Pleiades, though it lies in a quieter region near the Orion spur. Life within the arms is not only about creation. It is also about change. Massive stars born in the arms live short lives, often only a few million years, before ending in supernova explosions. These deaths scatter heavy elements into space, enriching the surrounding gas. The spiral arms are therefore not only cradles of new stars but also furnaces of renewal, shaping the composition of the galaxy over time. In contrast, the regions between the arms are quieter. Star formation still occurs there, but at a lower rate. The arms act as engines of activity, focusing the galaxy's processes in certain lanes, while the rest of the disk remains more subdued. This contrast gives the Milky Way its patterned look. Bright, active arms set against darker, less active spaces. The arms also provide variety in the types of stars they contain. While young stars and clusters dominate the visible features, older stars are present as well, flowing through the arms along their orbits. They add to the background population, blending their light with that of their younger companions. The arms are therefore not only sites of youth but also thoroughfares for stars of all ages, each passing through at its own pace. From our position within the Orion spur, life within the arms is partly hidden by dust and distance. Yet through telescopes, astronomers have revealed their richness. Radio waves, infrared light, and other forms of observation pierce the dust, showing the arms to be filled with nebulae, clusters, and glowing gas. The picture that emerges is one of quiet activity, steady and ongoing, repeated across the galaxy for billions of years. In this way, the spiral arms are both structure and process. They are patterns of density, guiding the flow of stars and gas, but they are also regions of life, where the galaxy's activity is most concentrated. To imagine the Milky Way without its arms would be to imagine a galaxy without its rhythm, without the places where light and creation are focused. Life within the arms is the galaxy's way of renewing itself generation after generation, across the endless span of time. The Sun, Earth, and all of humanity reside not in one of the Milky Way's great spiral arms, but in a smaller branch between them. This feature is known as the Orion spur, sometimes also called the Orion arm or the local arm. It is a modest structure compared to the Perseus or Scutum Centaurus arms, yet for us it is everything, for it is the region of the galaxy that cradles our solar system. The Orion spur lies between two of the larger arms. On one side is the Sagittarius arm, a region rich with star-forming nebulae and young clusters. On the other side is the Perseus arm, one of the brightest and most prominent structures of the galaxy. The Orion spur stretches between them like a smaller bridge, only a few thousand light-years across and about 10,000 light-years long. Though dwarfed by its neighbors, it contains countless stars, clusters, and nebulae, including those familiar in the night sky. Within the Orion spur lies the Sun, located about 27,000 light-years from the galactic center. This position is neither too close to the crowded central bulge nor too far out in the sparse outer disk. It is a middle ground, providing both stability and safety. Here, the solar system has orbited for billions of years, shielded from the extremes of radiation and gravitational disturbance that can occur nearer the center. In this quiet neighborhood, life on Earth has had the time and stability to evolve. The Orion spur contains several well-known features of the night sky. The Orion Nebula, visible even to the naked eye as a faint glow beneath Orion's belt, is one of the nearest and most studied stellar nurseries. The spur also includes the Pleiades, the Hyades, and many other open clusters, as well as bright stars like Betelgeuse, Rigel, and Sirius, the brightest star in the night sky. These familiar landmarks are part of our local spiral structure, making the Orion spur not only our home but also the source of much of the beauty we see above us. Though smaller than the major arms, the Orion spur is active. Star formation occurs within its clouds, adding new generations to its population. It contains both young stars and old, nebulae glowing with new light and clusters already beginning to disperse. In this sense, it is a microcosm of the galaxy as a whole, showing in small scale the processes that shape the larger spiral arms. The spur also serves as a vantage point. From here, we look outward toward the greater arms, seeing the rich regions of Sagittarius and Perseus as glowing lanes in the sky. Dust and distance obscure much of the view, but even through these barriers, the outlines of the arms can be traced. Our position within the spur gives us perspective. We are not at the center of the galaxy, nor at its edge, but in a place that allows us to observe and measure, to map and understand the larger system we inhabit. The quietness of the Orion spur has been important for Earth's history. Had the Sun formed in a denser region, the risks from nearby supernovae and unstable gravitational fields might have been greater. Instead, the spur has provided a calmer environment. Here, life on Earth has been sheltered enough to grow, while still close enough to active regions for the solar system to contain the heavy elements needed for planets and living things. The spur, in its modest size and quiet presence, has been the setting for the story of life as we know it. To recognize the Orion spur is to see that our place in the galaxy is not in one of its grandest structures but in a smaller, quieter lane. Yet this lane, ordinary by galactic standards, is extraordinary for us. It is the path along which the Sun travels, the region in which Earth was formed, and the place from which we look outward to the stars. The Orion spur is our home in the Milky Way, modest in scale but rich in meaning, a quiet corridor within the galaxy's larger spiral design. The spiral arms of the Milky Way are not just beautiful patterns of light scattered across the night sky. They are active participants in the long history of the galaxy, shaping how stars are born, how gas flows, and how the structure of the system evolves over time. Though they are not permanent objects, but rather patterns of density waves, their influence on the life of the galaxy is profound. One of the most important roles of the spiral arms is in the process of star formation. As gas clouds drift through the galaxy, the density waves that make up the arms compress them, increasing their density until gravity can take hold. In this way, the arms act as engines of creation, triggering the collapse of clouds into new stars. The bright clusters and glowing nebulae that mark the arms are visible signs of this ongoing process. Without the guiding influence of the spiral arms, star formation would be more scattered and less efficient, lacking the rhythm and concentration that the arms provide. The arms also help to distribute material throughout the disk. As stars live and die within them, they enrich the surrounding gas with heavier elements. Supernova explosions scatter these elements widely, mixing them into the interstellar medium. Over time, this process ensures that new generations of stars contain the materials necessary for planets and, in some cases, for life. The spiral arms are not only places of birth but also of renewal, continually recycling matter and spreading it across the galaxy. In addition, the spiral arms shape the overall appearance and stability of the Milky Way. Their structure, winding outward from the central bar, defines the galaxy's visible form. From afar, the arms are the most striking feature, giving the Milky Way its identity as a barred spiral. They are not fixed, but they endure for billions of years, maintained by the balance of gravity and motion. Their persistence ensures that the galaxy remains organized rather than dissolving into randomness. Interactions with other galaxies also influence the arms. Tidal forces from companions, such as the Magellanic Clouds, may stir the disk, enhancing the patterns of the arms. In the future, as the Milky Way merges with Andromeda, the spiral structure will likely be transformed, perhaps giving way to a more elliptical form. Yet until then, the arms continue to guide the galaxy's evolution, shaping the rhythm of its processes across cosmic time. The role of the arms is therefore both immediate and long-term. Immediately, they trigger star formation, provide structure to the disk, and mark the locations of the galaxy's brightest and most active regions. Over the long term, they influence the chemical enrichment of the Milky Way, the recycling of matter, and the overall stability of its structure. They are not merely patterns of light but patterns of influence, shaping the destiny of the galaxy in subtle but profound ways. To think of the arms in this way is to see them not only as features of beauty but as mechanisms of continuity. They sustain the processes that keep the galaxy alive, ensuring that stars are born, that elements are distributed, and that the disk retains its form. The arms are not eternal, but while they last, they guide the life of the Milky Way, serving as the framework upon which its evolution unfolds. The spiral arms remind us that the galaxy is not static. It is dynamic, filled with processes that change and renew it over time. The arms are both symbols and agents of this dynamism. They carry the galaxy forward, shaping its evolution, guiding its stars, and sustaining its light. They are the pathways of creation written into the disk, turning slowly but steadily through the ages. The Milky Way is more than a collection of stars. It is a system of patterns, cycles, and rhythms that extend far beyond human time. From its spiral arms to its central black hole, from the quiet drift of the sun through the Orion spur to the unseen halo of dark matter surrounding it all, the galaxy is a structure both immense and intricate. Every part plays a role. Stars are born, live, and die. Their remains are recycled into new generations. Arms guide the flow of matter, and the unseen framework holds the system together. To live within the Milky Way is to be part of this larger rhythm. The atoms of Earth, the elements of life, and even the air we breathe were forged in ancient stars, scattered by their deaths, and gathered into the cloud that formed the sun. The galaxy is not distant or abstract. It is the environment that has shaped us from the beginning, the quiet backdrop against which every story of life has unfolded. The journey through its parts shows a system that is not static, but always changing. Stars form in nurseries, shine on the main sequence, swell into giants, and end as white dwarfs, neutron stars, or black holes. Spiral arms guide star formation, while dark matter holds the galaxy in its grasp. Globular clusters orbit in the halo, relics of ancient times, while the sun makes its slow circuit around the center, carrying Earth with it through the ages. Yet despite this motion, there is steadiness. The Milky Way has existed for billions of years and will exist for billions more. Its rhythms are slow, its changes gradual, unfolding over spans of time so vast that human life measures only as a moment within them. To reflect on the galaxy is to encounter both immensity and calm. Immensity in its scale, calm in its continuity. As this story draws to a close, the image that remains is one of quiet endurance. The Milky Way turns, its arms glowing softly with new stars, its halo holding it together, its black hole anchoring the center. Around it, companion galaxies orbit, while the larger universe stretches outward in endless filaments. We are part of this structure, small but included, shaped by its processes and carried in its flow. To rest beneath the night sky is to rest within this larger story. Each star overhead is a reminder of the galaxy's rhythm, each cluster a fragment of its history, each faint band of light a glimpse of its spiral form. The Milky Way is both home and horizon, both origin and future, both pattern and mystery. Its quiet symphony continues, steady and slow, inviting us to listen, to reflect, and to find peace in its enduring presence.